about these, see what you think. This house water gets a little tricky here and there. What do you think about problem one? Which one is the false one? The third one, and what's false about it? It's actually timed up on that interval. Are we okay with that one? All right, how about number two? Third one again. And is it kind of the same reason? Yeah. We're concave up? Oh, don't worry, it gets tricky. All right, how about problem three? The third one, what's wrong with it?
It's concave down from -1 to 1 and concave up from 1 to 3.
Good deal, which means we have a point of inflection in there at x equals 1. Good. All right, how about 4? The second one. What is wrong with the second one? Yeah, it's increasing from maybe 5 to 6, but then from 6 to 7 it is decreasing, right? It's concave down on that whole thing, so the increasing decreasing is not right. All right, how about 5? A 0 is an x-intercept, and there is no x-intercept at 3. There's a function value at 3, -2, but it's not 0. So the second one is the false one. Okay, what did you do with number 6? What's wrong with the third one?
There's like I don't know, the other two were true, and I just did process.
Okay. Now what I really need everybody to pay close attention to is in statement 1, notice it says we are concave down when P of x is less than 0. That does not mean x less than 0. That means y less than 0, right? And where in the picture is y less than 0? Under my arm? So is every part of, and look at your picture, not mine, because yours is better. Is every part of the curve under my arm concave down? Yeah. So that's a true statement. He's talking about the y's, not about the x's. The graph is decreasing when x is positive. So x is positive to the right of my arm. Am I going down over here? That's a true one. Now, he said, I thought the first two were true, so the last one must be false. Why is the last one false? The graph is increasing and concave down when x is negative. So over here, is the entire picture increasing? Yep. Is the entire thing concave down? No. There's a little piece of it right here that is concave up. Right? Keep our beady little eyes open, don't we? Kind of tricky. All right, how about 7? What do you think about 7? Again, you have to read this really carefully because statement 1, the graph is increasing when y is positive. So is the graph increasing when y is positive? No, that part's not decreasing, is it? Or increasing, I mean. The graph is decreasing at n of 0. So right here, n of 0, are we going down there? that one's true. The graph is increasing. Oh, wait, I'm sorry. The first one doesn't say above my arms. The last one does. Go back to statement number 1. The graph is increasing when y is 0. So increasing here and increasing here. That first statement is true. It doesn't say greater than 0. It says where y equals 0. So y equals 0 here and here. And at both of those points, the curve is increasing. Now, the last one says y is positive. And that one is false because we're going down there. And how about the last one? What did you think about problem 8? Basically, -2 to 6 is pretty much the whole thing. So what did you think?
First one.
First one's not true. First one's not true. We are not concave down on the whole thing because we're actually concave up from -2 to about 2. Right? All right, let's put that away and get our notes out. Here we go. We're going to talk about average rate of change today. The average rate of change between any 2 points on the graph is the slope. To find the average rate of change, you need to find your y values and then calculate the slope. So, here we go. We're going to get in the habit. You can abbreviate average rate of change or write out average rate of change. And for problem number A, it's going to be f of -1 minus f of -2 over -1 minus -2. So that step has to be written every time you do an average rate of change. You're not going to do it in your head. You're going to write that step down. There will be a free response question on the exam, and that will get graded. So, f of the second, there's your average rate of change formula. And that's for the interval A and B. So it's f of the second minus f of the first over second x minus first x. Alright, so here we go. What is f of -1? Let's calculate that. F of -1 would be what? -1. What do we get? Did you say -2? I think that's right. And then what about f of -2? -2 over 1. So it looks like your average rate of change is -4. And in a real problem, there'd be a unit on that, like feet per second or dollars per hour or something like that. It's a rate of change, so something per something. We don't have that here. All right, you try the second one. Do the same thing. Write it out, so it'll be h of 4 minus h of 1 over 4 minus 1. So go ahead and calculate that. got 1/14. That look okay? Perfect. Example 2. Same thing, only now you're doing it from a picture. So your average rate of change is going to be g of 3 minus g of -1 over 3 minus -1. And now you don't have a rule, you don't have something, you know, a formula, equation, all you have is a picture. So what is g of 3? Look at your picture. G of 3 is 4. And g of -1 is 0. So it looks like our average rate of change is 1 feet per second or something. Okay, so the first ones we did, we had an equation, we had a function rule. Here we did it with a picture, now we're going to do it with a chart. Life expectancy of females, an average rate of change from 1850 to 2000. So, we'll do A of 2000 minus A of 1850 over 2000 minus 1850. So A of 2000 is 81.83. Wow, 46.10. I got 0.2382. What's that mean? Interpret that. 0.2382 what? Years? Years per year? That's a little confusing, isn't it? What does it mean? Every year that passes, a woman will live on average 0.23 years longer or 0.24 years longer. Does that make sense to you? So I can expect next year to live 0.24 years longer than I live this year. Alright, so how am I going to do that? 0.2382 what? Years of age per years of time passing. I don't know, what do you think? Is that okay? I can't say years per year, that doesn't make any sense. Does that make sense? Can we find an instantaneous rate of change? So keep in mind what you just did. You've got some kind of curve, and when you find the rate of change here, you're finding the slope of that line, right? So what he's asking you now is, can I find the slope of that line? Well, not in traditional ways, because what does it take to find slope? You need 2 points. You can't do it with 1 point. So what are we going to do? Do you have any thoughts about that? Well, let's look at my picture. Let's say I wanted the slope at this point right here. Could I approximate that slope by finding this slope? What if I found this slope? Can I do that? Which one do you think is better, the original black one or the brown one? The brown one. So in other words, I can squeeze in on that point, take a point on either side of it, make it real small interval though, and approximate my instantaneous rate of change. I can also use calculus to very easily find the instantaneous rate of change, but that's not part of our gig, so we are going to do it the long way. So, here we go. We want to find, here's our formula. By the way, what is this? Do you recognize this guy right here? This is your projectile motion formula, but the 4.9 tells me my measurement is in meters. Instead of being a negative 16, which it was when we did it in feet, this is in meters. Now we're gonna find the rate of change from 1 to 1.1. So in other words, I'm gonna fill in those blanks up there at the top. We can approximate the rate of change at a point by using the average rate of change over smaller intervals, increasingly smaller intervals. Okay, so this is a pretty small interval. So let's go ahead and find h of 1.1 minus h of 1 over 1.1 minus 1. So go ahead, calculate that. And then when you're done, calculate this one. And then if that wasn't fun enough, go ahead and calculate this one. All right, who got an answer to the first one? The A, the first big interval here. What did you get? 13 point. 14.79. Alright. 7-1. Okay. How about the second one here, smaller one? Well, 15.401. Alright, how about this one? You know what, I don't know if you thought about this or not, but since we have to plug a whole bunch of numbers into this, so I went ahead at y equals and put in this equation, y equals, and then I did second trace value, and I just tell it what number I want. So if I want the 1.001, it tells me it's 25.115195. And then second trace value 1 is 25.1. And then I can just subtract those. And I got 15.195.
I'm getting 15.15.
This one here?
Yeah.
Yeah, same.
Okay, let's check it. So, second value 14. So did I. It's easy to make mistakes when you're plugging those numbers in. That's why I like to use the value or my calculator if I'm gonna be doing a whole bunch of them. Just type that equation in the y equals like you're gonna graph it. And then second calc value, value. Or we can use a table function too, that we can print them all out. All right, so everything else look okay? All right, you need to make a decision based on example 4. What do you think is the true rate of change at time t equals 1? So this was within 0.1, this was 0.01, this one was 0.001, and then this one was 0.001 on the other side. Of 1.
Did you average C and D?
Oh, Ainsley says one idea would be to average these two because, like, if here's 1, this is 0.001 that way, and this is 0.001 that way. So she says, let's average those. Okay, I'd be certainly good with that. And I don't remember if I rounded that off or not. Did we round that off, or is that what that came out to be?
There was a 1 after it.
There was a 1 after it?
Yeah.
Did you get 15.2? That makes sense to me. This one is a bit lower than 15.2. Actually, this one is 0.049 lower, and this one is 0.049 bigger. I think that's a great great idea. Did anybody have a different idea? Yeah, I think that's a great idea. Good work. How are we gonna find the instantaneous rate of change as pre-calculus students? We're going to find the average rate of change on smaller and smaller intervals. Right? That's how we do it. It's tedious and kind of yuck, but that's how we have to do it. All right, the rate of change of a function at a particular point is the rate of change of the y values would change if the x values change. Oh, by the way, what's the unit on this? 15.2 watts. Meters per second. Yep. Yep. The rate of change is like a speed or a velocity. So while we cannot find the rate of change at a particular point in the APT calculus, we can estimate, right? Over a very small interval. We can also estimate using the concept of a tangent line. So finding the slopes of lines closer and closer to being tangent to the curve at that point. All right, example 5, here we go. We want to know if the positive or negative rate of change. One more time, rate of change is slope. So think about graphing it. Would your line be going up or down? The child's age versus the child's height. Positive, at least for a certain point when he stops growing, right? That whole first point, it should be positive. A golfer's skill level versus his score. Negative, because the better you are, the smaller your score, right? The height from the ground of a coin drop somewhere versus the speed of the coin as it falls. So the height from the ground versus the speed of the coin, dropping it from some really high point. Would you say that's positive or negative? As the height from the ground decreases, what does the speed do? That's negative slope. One is moving down and the other one is moving up. It's like the golfer's skill is going up and his score is going down. That's negative slope, negative correlation. Okay, so as the height decreases, we get closer to the ground. As the height decreases, the speed is going to increase, so that's negative. Looks like we've already done this, but let's practice it. The graph of f is shown above along with the line tangent to f at x equals -4. While we can't find the slope in AP calculus exactly, we can sketch the tangent line and estimate the rate of change. Okay, do example 6. Estimate the rate of change, the slope, at x equals -4, using the slope of the line tangent at x equals -4. So can we find a couple of points on that line? And sort of close to exactly. -2,5 looks like a point. And maybe -6, -1/2. We're estimating, so we're okay. is, what is that, 1.375? What did some others get? Close to 1.375? You good with that? Alright, sketch the tangent lines of the 5 points indicated on the graph. Okay, so he's plotted a few more points. Go ahead and just freehand in the tangents. Don't find the slope. Just freehand them in. Draw the tangents at the points that he did. And then he wants you to compare your tangent line at 4 and at 5. Does the graph appear to have a greater rate of change at x equals 4 or x equals 5? Why 5? Steeper, right? The thing's steeper, it's going up faster. Remember, rate of change is slope. The steeper the slope, the bigger the rate of change. Alright, next page. Connecting rates of change with the graph. If the rate of change is positive, the graph is increasing. Negative means we're decreasing. Going up, going down. If the rate of change is increasing, the rate of change is increasing, then we're concave up. Rate of change decreasing, we are concave down. Fill in the blanks, for example, 9. The graph of f is increasing and concave down because the rate of change is positive and the rate of change of the function is positive and the rate of change of f is decreasing. And then caution down at the bottom, this happens all the time. We have to read our problems so carefully. Are we talking about the function or the rate of change? Okay, example 10 is kind of like that sheet I gave you, that reference sheet. See if you can circle the right answers.
With rate of change.
I keep warning you, this can be so confusing, you have to read it so carefully. So let's look at the graph of F. The graph of F is positive. Why is it positive? Because it's above the x-axis. When we talk about F, we're talking about Y. And if F is positive, it's above the x-axis. So the graph of F is positive. The graph of G is negative, and the graph of H is positive. Okay? So that question doesn't have anything to do with anything except location. Where are you located? Above the x-axis, you are a positive function. Okay, back to F. The graph of F is decreasing. It's going down. The graph of G is increasing, and the graph of H is decreasing. All right, let's go back to F. The rate of change of F is negative. Remember, rate of change is slope. Which way is that curve moving? Down, so it has negative. So the rate of change of F is negative. The rate of change of G is positive, and the rate of change of H is negative.
What's the difference between the rate of change of F is positive or negative and the rate of change of F is either increasing or decreasing?
Okay, you can be positive or negative. You can be positive and getting smaller, or you can be positive and getting larger.
Yeah.
So when you're talking about the rate of change increasing or decreasing, you're talking about concavity. So go back to F. The rate of change of F is increasing because the thing is concave up. F is concave up. So its rate of change is increasing. The function itself is decreasing. But it's like going down at a faster rate. The rate of change of G is decreasing because G is concave down. So the rate of change is positive, decreasing. Going up, concave down. The rate of change of H is negative and decreasing because it's going down and it's concave down. Okay? There's no room for partial credit on those guys. You have to read the problem very carefully and then answer the question. All right, quickly, go to the back of the next page, the back of the Pamela page. The back of Pamela. Let's get question number 1A done, and then I'll go. The temperature of a pot of tea as it's cooling is given by the function h of t, okay? T is in minutes, okay? How fast is the tea cooling on average over the 10-minute interval? Show work and include units. Okay, so what's your work gonna look like? On average, over the whole 10-minute interval, won't that be h of 10 minus h of 0 over 10 minus 0? So h of 10 is 43. H of 0 is 66. I'm making a negative number. Does that make sense? Why does that make sense? Because it's cooling down. it's going down. Put a unit on it, negative 2.3, if I did my math right, negative 2.3, what? Degrees per minute. And that's degrees Celsius. All right, we will finish 1.2 next time, so you can go ahead and get started on that if you want. But I'm not gonna sign it till next time. But we're almost done with it. So feel free